Here, test. Hey, can you hear me for people online? Thank you. All right, good morning. Let's get started. Let's continue on the linear first order ODE. So we started already. So here is the general format here. So typically you see a first order ODE in this format, but we often do one step first. So we rewrite it into a format like this. Basically, we normalized the coefficient for the y prime term to be 1. Okay. So this is more or less the standard format we're going to deal with. And in the last class, we deal with the first case. We said that this is a homogeneous case. Or homogeneous equation. So that basically refer to when your input f of x is 0. So your first order differential equation just becomes simply like this. Then we have this so-called separating variable technique. Separating variable technique basically means you separate all the y together and then you separate all the x together. You integrate both sides. So we get the following results. So the y equal to basically a constant, then multiplied by e to the power negative px dx. Okay. So this is where we end up with from previous lecture. So we said B depends on initial condition. B value could be positive, could be negative. So B could be either values. So I'll show you one graph here from my lecture notes. So this is the graph of this is graph here. Let's bring it over here. So this is the graph of this y function at here for right. I mean, this is actually specifically. Actually, I jump ahead a little bit here. Okay, let's just sorry. Let me. So skipped a couple of details, quite a few details actually. So let's take a look at example together. Right? So let's say this is a first order differential equation. Y prime equal to 2xy. This is a linear because if you rewrite it in this format, so you put everything in one side. So apparently this is a linear first order ODE, but also it's homogeneous because there's no input into it, right? So in this case, we can apply the separating variable technique. So I write it into this format just to show that this is linear. But when you use separating variable technique, you actually use this approach here. So this is dy over dx. This is 2xy. So then you put all the y together, and you put the x together. Okay. When you put the x, y together, of course, we never put this dy or dx on the denominator, okay, because you're gonna have to integrate, right? Then we integrate both sides of the equation. And that's very simple integration. So you get ln absolute y equal to x squared plus constant c. Did I miss a negative? Oh, sorry, I missed a negative here. There's a negative sign in front of the negative here. Just put a negative here. Okay, okay. So then you can take the e to the power of both sides. Not changing anything, e to the power of both sides. So you get absolute y equal to, technically, absolute y equal to e to the power negative x squared and the e to the power c. So I'm still kind of not skipping any details here. So e to the power c is a constant. So you could just call it a at here. And then y equal to positive negative of this. So positive and negative, basically a here, right? You could just rewrite it as a one single constant. Okay, so without initial condition, so we don't know. So we'll just keep it as a one single constant. So that's it. That's your general solution for this question. Okay. And then from here, you can plot this function by giving the b value with a different numbers. Can be positive number, can be a negative number, right? So those, the ones on the top of the x-axis refer to a positive b number, and then this is less than 0 for any of the curve underneath the x-axis. And of course, you know, the larger the b, then the curve goes up more, right? So that's the implication of the b here. But as I said, the b often in time can be determined. So this constant here can be determined by initial conditions. So a lot of time, most of the time, the question will give you an initial condition. Okay, so now what's the initial condition, right? That's the basically next question here. So sometimes we call this, in general, this is initial condition problem. And it's very simple. Initial condition basically means when you have a differential equation, right? Often in time, so for example, for this initial condition, for this differential equation. So let's say you're given this initial differential equation, and then at the same time you're given, so you say, okay, y at x equal to, for example, 2, okay, equal to 1. Okay. So you have an additional information given, okay, associated with this differential equation. So this is called initial condition. I mean, a lot of time you might argue, so x equal 2, why would you call that initial? So it depends, right? Maybe you consider x equal to 0 as initial, but if that question just give you x equal to 2, okay, so that we consider that as initial condition. Or the writing can be a little bit different. It could say is at x equal to 2, y equal to 1, right? That sort of things. Yeah, but it's the same meaning. Okay, so the 1 here, okay, so the 1 here, so we call this initial value. So that's basically, that's how it started, something like that. So if I were given this initial condition, then I will be able to determine this B value, okay, by substituting this initial condition into this answer, so the final answer right here, to solve for the B. So how we do it, I mean, the number here is very arbitrary, so it may not actually be very accurate. So what you could do is you substitute x equal to 2 into that equation. So you substitute 1 on this left side, and then you substitute on the right side. So you get b to the -4. Okay. So then you solve for the b. So you get b equal to 1 over, so this e to the power 4. Right. So that's based on this condition, you get this b value. That's how you use this initial condition and initial values. So initial condition, we will simplify this, call it IC, the IC problem. Okay. So let's take a look at one more examples of illustrating this initial condition problem here. Okay. Yeah. Now, before we see another example here, I want to go back to this general solution. Okay. So this general solution here, and how the general solution can be altered to reflect this initial condition problem. So this general solution y equal to b e to the power negative px dx. Okay. This one I would say can be modified if initial condition y x equal to a is given. Okay, so even more specific, let's say y at x equal to a equal to b, for example, right? That's an initial condition. So if you're given this, then this general solution can be modified into the following format. So this y equal to b e to the power integrates the integral sign here, the limit. Originally, this is a indefinite limit. So now, because I have initial condition, which I know the x starts from a, so you can start the limit from a. And then you end up this limit with an x, integrand still the px, but this time we'll change the x to dummy variable u. Okay. So, any other dummy variable. So this general solution can be modified if the initial condition is given. Then it's modified into this format right here. So you might wonder, how could you do that, right? It's actually quite straightforward, because first of all, if you compare this, okay, with this px dx, okay, if you compare these two integral, okay, can anybody tell me what's the difference between these two? Yes. Sorry, louder. What? Not quite like that. I want you to think from antiderivative perspective. For example, let's see if the antiderivative p of x is capital P of x. Okay, if it's capital P of x, so then what would you get if your limit is given here? What's the fundamental theory of the calculus? Exactly, right? So this one here, you get px minus p of a. And what about this one? In general, this is, that's right. So what's the difference between these two? Not much difference, right? So technically, this one here, the capital C, can consume this P of A because P of A is a special number. Okay, so not much difference. So if you see the difference, you could see the difference between these two, maybe just constant. It's a C, it's the difference between C and the P of A. Okay, yeah. So that's the difference between this original general and the current specific modified version of here. Okay, but how's that initial condition being played into this equation then? So let's substitute the initial condition into this new format here. Okay, so then if you look at this one here, my initial condition is given at x equal to a. Then based on the modified format, okay, so I say x equal to a. Okay, then what happens is what? You get the integral here becomes a to, what's the upper limit now? No, x equal to a. So the upper limit is a, right? Because now your x is a. So then your integral here, when your integral limit is a to a, the same limits, the whole integral is equal to 0. So you get e to the power 0, which is 1, so you get a b. And this b here is your initial condition, small b. Okay. So that's the same idea. Okay. Oh, good. All right. So I mean, I don't need you to remember this formula here. Technically, a lot of time when you solve for initial condition, you could just solve it based on the results here. Okay. But that's a connection between a general solution without initial condition given compared to a solution with an initial condition given. Okay, that's just the difference. Let's take a look at one more example here. So let's look at the RC circuit. And this RC circuit has no input. And we have shown the equation for a typical RC circuit with the voltage input. So now you just have to get rid of the voltage input. So we can derive this equation, the differential equation for this system, right? For this system to this first order differential equation. So let's solve this one here. Now, before we solve, we are given initial condition, VC at the initial value equal to V naught. So basically at t equal to 0. So then we already have the solution, right? So this is if I plot a solution, we get solution for this equal to a, any constant, or just use a b here, e to the power negative rc to the power of it, 1 over rct. So I want you to try it yourself. I mean, this is basically your function. In that case, we call it p of x, but this call it p of t. It's the same thing. So use separating variables, and you can get this solution at here. And now once we get this solution, let's apply the initial condition to get this capital B value. Okay. So you substitute t equal to 0. So basically you get VC0 equal to B, and then substitute t equal to 0 here. Yeah, when you substitute t equal to 0, it's B, so that B equal to V naught. So your VC of t equal to V naught e to the power of negative RC, okay, times t. So I'm singling this out, this example here. Actually, if I recall correctly, there are quite a few, there may be a couple labs that you will do that's directly related to the RC circuit. Okay. So if I plot this curve, the curve will be an exponential decay curve. It starts from V naught, and it will decay to not going to be 0, but it will decay absolutely close to 0. That's RC circuit. If you have an initial charge on the capacitor, then the charge will disappear, but it won't disappear completely, right? There will be a little bit, always a little bit on it. Cannot be 0, approach to 0 infinitely. This one over RC at here. Okay, there's a very important property. So you can define this RC value as a tau, and this one is called time constant. Okay. So what's a time constant? So time constant basically is that how much time it takes to drop to, so this value here is 63% of the original V naught. So how much time it takes to drop to that? So this tau right here, this is RC. This RC value. And in the control system, and you actually often use this as an important threshold here. It's a time constant. You often check, how much time in control system. Sometimes we look at this step output. So how much time it takes to reach the standard input, often is 1. Okay. So this value here, okay, give you that 63%. It's called time constant. And the next time, if you have a first order, if somebody asks you what's the time constant, right, how would you find it? You find the time constant, try to look at this one here. So whatever the coefficient in front of the t, okay, and then you 1 divided by that coefficient of this t, and you get the time constant. Right? Because 1 divided by 1 over RC give you RC, right? Yeah. Okay, so that gives you some idea of what's so-called the initial value problem, and we will actually apply this for any one of the future differential equations. Okay. So that's pretty much about case number 1, when we have this homogeneous equation. So case number 2, go back to my original first order differential equation right here, is we're going to deal with non-homogeneous case, which means the Q of X is not 0 anymore. So we're going to have everything there. So y prime plus px y equal to Q of X. So Q of X not equal to 0. We're dealing with a non-homogeneous case. So let's see how we can solve a non-homogeneous first order differential equation. So to solve this type of differential equation, we use a technique called integrating factor methods. So a question from online here. What's the small b? Small b is the initial condition, right? That's given here. So at x equal to a, y equal to small b. Initial value. So let's take a look at what is this integrating factor method. All right. So this is where we're starting from. Okay. So this equation here is where we start. I'm going to multiply this equation, multiply both sides of the equation with an unknown function of x. I call it sigma x. This is a small letters, Greek letter sigma. That's how you write it. Let's multiply this function to both sides of y prime pxy equal to q of x. So then what we get is we get sigma x multiplied by y prime pxy, oh, sorry, sigma x px y and equal to sigma x q of x. Right. And you'll see why we want to do this, right? Now, once we get this step, the next step is we want to find an appropriate function sigma of x, okay, so that the left side, okay, so the left side, which is this two terms here, can be rewritten as sigma times y prime. That's objective. And you might wonder, how could you do that, right? So, and yes, it could. So you'll see why. So sigma x prime, just for your case, I mean, this is basically, because right now we're considering the whole thing is function of x. So you're just taking the derivative of sigma y, sigma times y, with respect to x. All right, so now the question is whether we could do that or not. What is that function sigma of x, right? But before we try to find that the sigma x at here, let's assume, okay, let's just assume that you have a sigma of x so that the left side is written into this format. Okay. So take it take a leap of faith at here, right? Just see if possible, then what happens? So let's try this way here, right? So if that's possible, then how's that making our life a little easier to solve this first order differential equation? So then if this is possible, right, the original differential equation, so which is this one here, okay. And what does it become? Okay, so because I said I somehow find a function sigma of x, and my left side is changed into a d over dx sigma of x times y and equal to sigma of x times q of x. Right. So I don't know what sigma of x yet. I'm just saying, suppose we have find that sigma of x, and my differential equation, right, becomes this derivative equal to this. And then you look at, if you look at this whole thing at here, then I could multiply the dx to the right side. Okay, so then I get d times sigma of x y equal to sigma x qx dx. And from here, and you can see on the left side, it's a d, a bracket, whatever inside the bracket, right? Then you can integrate. You can integrate both sides. Okay. And when you integrate the left side, d anything, you're supposed to get back whatever inside the bracket. So integrate to d of whatever function, right? You get back this sigma x times 1. And the other side, because we don't know what sigma of x yet. This is a general case, so we'll keep it as it is. Okay. So then technically, there should be a c at here. Okay. So finally, you can see you can solve for the y now, right? How do I solve for the y? Basically, you divide by the sigma of both sides. Okay, I said that. I haven't found a sigma of x yet, but I'm just giving you a glimpse of how this sigma could give us a solution for the answer at here. Okay. All right, so that sigma is the key here. So if we can find a sigma, then we solve the problem. Okay, that's good. So now let's get back to the sigma here. So basically, let's say, how do we find this sigma? And the sigma here is basically what we call the integrating factor method. So now the question is how to find this function sigma x. And the sigma of x is called integrating factor. It's called integrating factor. Let's go back to this step here. Okay, so this step is a critical step. We want to write this left side into sigma y bracket prime. So let's go back to that side. Basically, we want, right? That's what we want. This sigma y prime equal to sigma x y prime plus sigma of x p of x y. So bear in mind, this is what we want, right? Yeah. So from here, let's look at what is a sigma y prime. What do we use? We use a simple product rule to expand this sigma y prime. So the product rule says sigma prime y plus sigma y prime. And so this is your left side. You want this. Now basically, instead of you want sigma y prime equal to this, so then you want this equal to this. So now you can compare now. Let's see, compare the left and the right. And you happen to have this term exactly the same. So you can cancel them out. And then you're left with sigma prime y equal to sigma x, px, and y. And of course, this y and y will cancel out. So you're basically left with, now I'm going to rewrite the sigma as d sigma over dx equal to sigma x px. Okay. And from here, we're remember what we're trying to do, huh? We're trying to find which function? Sigma. So basically, you look at this equation here. This is literally, what kind of equation is this? Yes. ODE, first order ODE here, right? And it is also the simplest one, the homogeneous. So you can use the separating variable technique to solve the sigma. So I'm separating all the sigma together and then separating the rest of the term together. So from here to here, it's the separating variable technique. And then you can integrate both sides. You get ln sigma absolute value equal to the px dx at here. Okay. Then you take exponential power of both sides of the equation, right? Same approach as when you solve homogeneous equation. And you get absolute value of sigma equal to e to the power p of x dx. Okay. So technically, sigma should be positive, negative. Technically, you should have another constant c at here, right? And then you get positive, negative a e to the power px dx. Okay. Now, however, remember, this is finding a sigma. This is not finding a general sigma. Basically, what you're trying to find is you only need one candidate for the sigma function. Okay. So basically, you don't need a general. You only need one sigma of x. If I only need one sigma of x, then I can pick the simplest one. I think what I would pick is I will pick I'll get rid of the constant a. I'll just pick the e to the power of this integral here. With that one candidate, that should be fine, because I'm not looking for an arbitrary solution for the sigma here. So that sigma is basically this equation in here. I mean, you can call this as a formula, but I don't want you to try to memorize the formula. I want you to be able to go through the process here to solve for the sigma, okay, for this stage. Because going through the process will help you understand how the integrating factor is obtained. And you also kind of may be prone to less errors. But in general, right? So this is your solution for the sigma. What does it mean is, of course, if we have p of x, we can solve for this. What does it mean is if I plug the sigma back over here, okay, or basically back to the first step, when you multiply the sigma to both sides of the equation, then the left side can be written into sigma y prime. It's very much like, so now you probably should have a little bit clearer thinking now, is that what's the purpose of multiplying the sigma here is because once you do that, you are sort of reversing this product rule, right? The product rule is when you multiply two functions, taking derivative, right, you got u prime v, v prime u. So your idea is you try to rewrite the left side of the differential equation into a one single product rule, right? Sigma y prime. So that's the idea of the sigma here. Then from here, you can integrate. So that's why this is called the integrating factor. Okay, so then you can separate variable, you can integrate. So overall, this approach right here, right, for this kind of non-homogeneous first order differential equation, what's involved here are two steps. Number one step, you're gonna have to find the appropriate sigma function. Number two step, then you need to solve for the y, okay, based on the steps listed here. And that's the two steps involved here. So let's take a look at examples together. Here we have a first order differential equation and non-homogeneous because the terms on the left side, on the right side is non-zero. And we're required to solve for the y. The question didn't give us any initial condition, but that's fine. So we'll keep the solution to be general innate. Okay. Before you proceed at here, so I want you, this is actually a pitfall often in time. The given differential equation, the coefficient for the y prime is x. But the approach that we have listed, okay, is based on a differential equation where the coefficient for the y prime is 1. Okay, so this is basically the standard format we have worked on. Then if you see a differential equation like this, first order, okay, the first step is you should normalize this equation, okay, so that the coefficient for the y prime is 1. And normalizing it is very straightforward. You just divide everywhere by x, then you get rid of the x in front of the y prime. So normalize. So you get y prime plus 2 over x times y ln x, x cubed, then 2 over x. You can call it normalized or whatever you call standardized. Okay, that's fine. Either way is fine. Oops. The reason basically, I just want to write it here. We are putting it into this format, right? The standardized format. Okay. So you have a clear knowledge that which term is P of X and which term is this Q of X. Because if you try to memorize formula, then you have to know exactly what's P of X and Q of X, right? Yeah. Okay, then step number 2, we start to use this integrating factor method to solve this question now. So I'm not using any formula, I'm not skipping any step, I'm basically gonna follow exactly all the steps to solve this question. So we're going to multiply this sigma of x, okay, to both sides of this equation here. Okay, so we're going to get sigma of x y prime plus sigma x 2 over x y sigma of x times ln x x cubed sigma x 2 over x. What is the idea of doing this step? Okay. Just jog your mind. We want to rewrite this into this. We want to rewrite this into this. And to achieve this step right here, so we need, what do we need? You can go back to this step right here. Okay. So you see, this is what we want, right? So basically you need, this is the key here. You need this one here. Okay. So once you expand this product rule, and you need the d sigma dx equal to sigma x times p of x. Okay. So we need this. So from here, we have d sigma over dx equal to p of x times sigma x times p of x. So sigma x times p of x. What is p of x? You go back to your standardized function. It's 2 over x. Right, so 2 over x. And now we are going to use a separating variable technique to solve for sigma. So then you get d sigma over sigma equal to 2 over x dx. and then integrate both sides, right, as 0. We get ln sigma equal to 2 ln x. So notice that I now get rid of the absolute sign now, because remember I only need 1 sigma, right? So here you can neglect some of the details, a little bit less rigorous. Okay, so then you take exponential of both sides of this equation. And you get sigma equal to, what is the result for the right side? X squared. So sigma equal to x squared. Right. So that basically means when sigma equal to x squared, you put x squared here, then your left side can be written as x squared times y prime. And this is also important, is that you should ask this question: how do I know I get the right integrating factor sigma? How would you check? This is how you check. You plug in your sigma back into your left side of the equation at here. And you also have the sigma y prime here. Just verify, right? Verify that sigma y prime will actually give you back the left side of this equation. So you can verify like this: x squared y. What is x squared y prime? Product rule. So 2xy plus x squared y prime. Okay. So that's what you get using the product rule. So what do I get for the left side when I multiply the sigma x to the left side? And you can see here, which is what? So let's see. Let's rewrite it here. So sigma x times y prime plus sigma x times 2 over x times y. So plugging x squared here, so x squared y prime square, so 2xy. So that's exactly the same, right? So that's a verification that you got the right sigma. So check. All right, so once you get the sigma, then the next step, remember this is the first step, and the next step is to solve for the y now, right? Solve for the y, okay? So because your left side is sigma y prime. Okay. So I'll just write it as d over dx sigma times y. Now I'm confident my left side is written into d over dx sigma y. Okay. So then what does this left side equal to? So you go back to your original function. This is your right side here. So your right side equal to sigma x, okay, ln x, x cubed plus 2 over x. Time to substitute the sigma x into this equation. When you x squared over here, substitute x squared. And this side is d over dx, x squared y. And then you multiply the dx to this side here because you can see clearly this side is all about x, right? So d x squared y equal to x squared ln x, x cubed plus 2 over x dx. And now I'm going to integrate both sides of the equation at here. So the results for the left side is x squared plus y. And then here you can certainly simplify a lot. X squared, simplify this to be a x here, and it's 2x here, dx. So this is time to test your integration technique now. Okay, so how do I integrate the first one? The second one is fairly straightforward, right? Plus C. Second one is x squared. How do I deal with the first one? Right. Substitution rule, right? So you're letting u equal to ln x. Is that what you're saying? Yeah. So substitution, basically. Yes. But I usually do this. So this is ln x at here. The 1 over x basically is d ln x. Okay. So d ln x give you 1 over x. And now you can see I have exactly the same thing, ln x, d ln x. So then your overall results should be, here is 1/2 ln x squared. Okay. Plus the x squared plus the c, and x squared y equal to this. So finally, divide x squared by both sides. You solve for the y. Okay. So that's the procedure, right? So at this stage, I want you to not skip any, to not memorize any formula, to not skip steps. Follow each one of the steps in here, completely understand the integrating factor methods, okay, when you practice. I'll show you a couple more examples next lecture. All right, I'll see you next Monday. Oh, actually, sorry, next Monday, we're canceling the Monday's lecture to compensate for your night evening midterm. Okay, so the lecture was to resume on next Wednesday.